Ever wonder how they make sour candies sour? Let's dive into the concept of acids and bases to find out why. Welcome to the flock. At some point in your life, you've probably heard somebody mention that lemons are acidic. But what does that mean? What does it mean that lemons are acidic? And what color would lemon juice then make pH paper turn? We use pH paper to measure acidity or basicity. So to determine which side of the scale is acid or base, let's try putting some pH paper into lemon juice. Drum roll, please. So since we know that lemons are acidic and our litmus paper clearly indicates red for lemon juice, we can assume that the red side of the spectrum would represent acids. Well, then what about the other side? Well, if it's not an acid, then it's a base, or it could be neutral if it's somewhere in the middle. So the other side of the spectrum, the purple and blue side, represents bases, and somewhere in the middle, that neutral area is green. But how is it that this pH paper can measure the pH? How is it that it can change color and tell us if it's an acid or a base? Well, shockingly enough, this isn't the only thing that can tell us if something's an acid or a base. We can also make solutions out of everyday items like poinsettia flowers. If you hadn't seen my previous video on that, check it out in the description below. I show you how to make it. Or red cabbage juice can do the same thing. Or even fruits and vegetables like onions, grape juice, peach skin, radish skin, plum skin, beets, and berries. These are all things that change color according to pH, i.e. pH indicators. They can all tell us whether something is an acid or a base, which we still don't know what the difference is between an acid or a base. We'll get to that. Hang tight. But first I want to show you how even something like red cabbage juice can be used to indicate acids or bases. Notice that according to the red cabbage juice, our acids will still be on the reddish pink side, our neutrals will be purplish blue, and our bases will be this turquoise bluish green color. Let's see this concept in action. Safety first, always wear goggles when dealing with acids and bases and any chemical. So what I have here is some red cabbage juice that I just took some cabbage leaves from and boiled in water, and that basically turns the water purplish like this color of red cabbage. As a baseline, let's try something that we know is neutral, filtered water. We're just going to add this cabbage juice to the filtered water and see what color it is. Since we know that filtered water is neutral, we can assume that this is a pH of 7, right in between a pH of 0 and 14, which is what our pH scale is measured on. Now let's try something we know is acidic. We just tried the lemon juice earlier with our litmus paper. Let's try it with the cabbage water. We can clearly see that it turned a deep pinkish red. How about vinegar? Also a deep pinkish red. We can assume that vinegar is also an acid, just like lemon juice. How about hydrochloric acid? We already know from the name that this should be a red-pink color because it's hydrochloric acid. But let's test it with our red cabbage juice. Now, I'm not sure if you can see that, but it's actually fuming. So this is probably the most concentrated acid that I have at 10.2 moles per liter. So this is probably as red as you're going to see red cabbage juice get in terms of pH indication. In other words, this is the most acidic thing that I have at home. How about magnesium citrate? Magnesium citrate is something you can take to help you go to sleep and to help you go poop. Looks fairly purplish to me. I would say that that's probably somewhere in the neutral scale. How about whole milk? My daughter's favorite diet. That looks like a light purple, also somewhere in that neutral range. Next up, some baking soda water. Ooh, pretty blue. We're starting to get towards the 8 pH if you're comparing it to the scale there. So we're getting a little bit more basic. Next we have this little tiny beaker of Windex. It's a cute little beaker. Ooh, another really pretty blue. It definitely looks to me like that's between 9 and 10 pH. And we also have some degreaser. This one looks a little bit more green to me than the Windex, so probably a little bit more basic. And just because COVID is a thing and hand sanitizer is practically our life now, let's try hand sanitizer. Looks like that would be around a pH of 5 or 6, somewhere in there. At the beginning of the video, we mentioned shock tarts. Why are they sour? Why do they taste sour? Well, let's figure out if it's an acid or a base by using the cabbage water. I just have some water in this cup. I'm gonna put a little shock tart in there, swirl it around. Let's see what the cabbage water will tell us about shock tarts. Are they acidic or are they basic? As you can see, the water is more on the pinky red side. That means that shock tarts are acidic.
That means acids must be sour, just like lemons are sour.
Just saw with the cabbage water, there's a range on this pH scale. There's 0 to 14. When we're on the 0 to 6 side, we're talking about acids. When we're at 7, we are neutral. And from 8 to 14, that's the basic side. Notice that our cabbage water was pretty accurate. The lemon juice was a pH of around 2, and the vinegar was a pH of 3. Milk was around a pH of 6. Baking soda was right there in that base range. And ammonia, our Windex, was definitely basic, along with the degreaser. We're going to be building an alliteration for bases for you to remember. The first part of this will be that bases are blue. So enough about all these colors and the whole pH scale. What does it mean to be an acid in the first place anyways? Well, as we found, acids are sour and they're often thought of as pretty dangerous chemicals. However, they tend to not be as dangerous as bases in actuality. As we saw with the cabbage water, or you could have done the same thing with poinsettia petals or berries or pH litmus paper, they change color based on what they come in contact with. They can react with metals to produce hydrogen gas, which is flammable by the way, and really fun to light on fire. They neutralize bases via a neutralization reaction to create water and a salt. They can also create electrical current, i.e. you could light up a light bulb with them, and it's easy to identify them because they often end in ic acid. For example, hydrochloric acid. Here's just a few common acids you should be aware of. That bottom one, C6H8O7, is citric acid. And citric acid is often the chemical that companies use to make their candy sour. However, in the case of shock tarts, or sweet tarts extreme sour, they use malic acid instead. Bases, the blue side of our pH scale, are also referred to as alkaline. And since acids taste sour, bases taste bitter. That's our second alliteration. Bases are blue and bitter. And they actually tend to be more dangerous than acids are, more caustic that is. Just like the acids, they can change color with indicators, and they neutralize acids, as the vice versa of acids neutralizing bases. When they come in contact with your skin, they can feel slippery. For example, if I was to get lye, oven cleaner, true story here, happens often, on my fingers, then it literally starts to dissolve my skin cells and they slough off my body, and when you rub your fingers together, they feel slippery. Don't worry, I don't do that just for funsies like on a Wednesday night. I used to have a cleaning company, and I've cleaned hundreds of ovens. They can also conduct electrical current just like the acids do. Some common bases you should be aware of are sodium hydroxide, NaOH, that's the oven cleaner I was talking about, NH3, ammonia, our Windex, and NaClO, that's sodium hypochlorite. That's the stuff that makes bleach work. There's a few ways that we can measure this pH, this scale that we use to determine if something is an acid or a base. There are 3 ways in which we can measure pH. The first way is a qualitative way, indicators, like our cabbage juice. These are the solutions that change color and are sensitive to pH change. They show you a color when it comes in contact with an acid or a base. These indicator solutions are themselves either weak acids or weak bases. Why does this change color to begin with? It's because the color of the solution is changing when the acids are giving away their protons, their H ions, or the bases are accepting protons, H ions. The other qualitative measurement, meaning that it doesn't have a number associated with it, is the Litmus pH paper you saw at the beginning of the video. These strips of paper are coated with an indicator, sort of like the indicator solution, just soaked onto paper. And these change color in the same way that the indicator solution does, to indicate whether something's an acid or a base. And the only quantitative way to measure it is via a pH meter. Remember how I said that acids and bases conduct electrical current? Well, this pH meter basically measures the voltage difference between two electrodes in solution. That's what this little wand thing is. It's literally an electrode, and it sends that information to the meter, and the meter gives you a numerical value. Since it can give you a digital numerical value, this is the only quantitative, or the most accurate way to measure pH. It's important to know that this pH scale that determines acidity or basicity is a logarithmic scale. Log. Each number on the pH scale, that 0 through 14, represents a 10-fold change. So when you go from 1 to 2, that's 10 times. So when you go from 2 to 1, that's 10 times more acidic. Or if you were to go from 11 to 12, that's 10 times more basic. Before we move on, I want you to test your understanding of that concept. Let's say we have vinegar at a pH of 3 and battery acid at a pH of 1, which is, by the way, why you should wear goggles when you jump your car battery. You don't want pH of 1 in your eyeballs. You'll go blind. But if we're comparing those two chemicals with a pH of 3 and a pH of 1, how many times more acidic is battery acid than vinegar? Pause the video here and think about it. Hopefully you understood that a jump from 3 to 2 is 10 times more acidic, and a jump from 2 to 1 is 10 times more acidic. So 10 times 10 would be 100 times more acidic, i.e. battery acid is 100 times more acidic than vinegar. Okay, we know that acids are sour, we know that bases are bitter, and they're blue, and acids are red, but what are they intrinsically? What is it that they do chemically? This dude, Arrhenius, in the 1880s, gave acids and bases a definition as follows. He said that acids are the ones that are going to make hydrogen ions, H+, also known as hydronium ions, when dissolved in solution. So if you took a chemical and you saw that it made protons, hydrogen ions, or hydronium ions in solution, it would be considered an acid. He also defined bases as ones that produce hydroxide ions in solution, OH-. So if you were to take a chemical, dissolve it in water, and it gave you OH ions, it would be a base. So for example, if we took HCl and dissolved it in water, we would see that it would make H+, or protons, we also call them. And that means that HCl is an acid. If we took NaOH and dissolved it in water, we see that it breaks apart into Na+ and OH-. That's our hydroxide ions. Therefore, we know that NaOH is a base. Now that you've seen me try it, go ahead and pause the video here and give this one a try yourself. We see here that HF dissolved in neutral water creates H3O plus hydronium ion and F- in solution. That's what that AQ stands for, aqueous. Since it makes H3O plus hydronium ion, according to the Arrhenius definition of acids and bases, HF would have to be an acid. How about the bottom one? We take ammonia, NH3, and we put it in water, which is, again, neutral, and it creates ammonium, NH4 plus 1, and hydroxide ion, OH-. According to Arrhenius, since it creates OH-, we know that NH3 must be a base. So then, if Arrhenius said that acids make hydronium ions, or protons, H ions, and bases make hydroxide ions, what happens when those two meet up? We end up getting H plus OH. In other words, we make HOH. What is HOH? You'd probably recognize this better as H2O. If we write it as HOH, it's the same thing. There's still two H's and one O. So it makes water. This is the reason why when we react acids and bases in a neutralization reaction, we always create water and a salt. And if we perfectly neutralize any acid with a base, we know that right in the middle of the neutral pH scale is water. So something that trips up a lot of students is that not only do we have acids and bases, but we have this thing called strong acids and bases and weak acids and bases. Now, don't get confused here. The strength of it has nothing to do with the fact that they go to the gym, get buff, and drink protein shake. That's not what it's talking about. We're not thinking about strength here, strong versus weak, in terms of physical strength or the damage it can do to you in terms of how harmful the chemical is. It actually has something to do with a process of dissociation or ionization. Let's check it out. Let's use this PhET simulator to see if we can determine the difference between strong and weak acids and strong and weak bases. Let's start with this neutral water at a pH of 7. We see the water equation down below, that two waters can react with each other to create hydronium ion, that's our acid part, and hydroxide ion, that's our base part. Notice that there's equal amounts of hydronium and equal amounts of hydroxide. That's what makes it neutral. There's an equal amount of acid to an equal amount of base. But let's switch our solution to a strong acid instead. Here we clearly see that when we have a strong acid, HA, dissolved in water, H2O, we create a salt, A-, and H3O+, hydronium ion. Now there's a lot of hydronium ion in there, and it's at a pH of 2. What's the difference between this strong acid and, say, a weak acid? For the weak acid, we don't have nearly as much H3O plus hydronium ions, and we're at a pH of 4.5. What we do have an abundance of here for the weak acid is a lot of the HA. In other words, the starting acid on the reactant side. It's almost like it didn't get converted over to the product side. How about the strong and weak bases? For a strong base at a pH of 12, we see the same kind of pattern going on. For MOH, that is our base, we see that when we dissolve it in a solution, we create M, our salt, and OH minus our hydroxide ion. Now there's a lot of hydroxide ion, and I don't see a single MOH anywhere in here. What about for a weak base? For the weak base, we see the pH goes to 9.5, and we see that there's a lot of these little B spheres throughout. Our base, it's almost like the base hasn't reacted with the water in solution, and there's far less hydroxide ions present. Hopefully you're getting the idea here that the strong acids and weak acid difference is that the strong acid creates all of that H3O plus in solution, whereas the weak acid stayed as HA. And for the bases, it was a similar trend. For the strong bases, we created a whole bunch of hydroxide ion in solution, and for the weak base, we had a ton of just the normal B that didn't react with the water. So now let's see what increasing or decreasing concentration, i.e. molarity, moles per liter, would have as an effect on pH. If we're starting with a strong acid at a pH of 2, and we have a concentration of 0.01 moles per liter, let's increase the concentration and see what happens. Whoa! So all the way up to 1 mole per liter, we end up with a ton of hydronium ions, and our pH dropped to 0. Remember, the pH scale is logarithmic. Going from 2 to 0 is 100 times more acidic. Let's try the same thing with a strong base. If we start at a concentration of 0.01 moles per liter, we have a pH of 11.99, so basically 12. Let's increase the basicity to 1 mole per liter, that concentration. Whew! Now we have a pH of 14. Again, a twofold jump. That's 100 times more basic by increasing the concentration. Now, both of those examples were with strong acid and strong base. Let's try weak acid next. We have 0.01 moles per liter as our concentration to start with, and we have a pH of 4.5. If we increase the concentration to 1 mole per liter, we see that the pH went to 3.5. So not quite as big as a jump as the strong acid did when we increased the concentration. However, it still did become more acidic as more hydronium ions formed in solution. Let's try it with a base next. If we have a weak base at a pH of 9.5 and a concentration of 0.01 moles per liter, and we increase that concentration to 1 mole per liter, we see that we created more hydroxide ion in solution, and our pH went up to 10.5. It became more basic. However, the same trend holds true. it didn't jump 2 whole log scales like the strong acid and strong base did. So although it became more basic, it didn't jump quite as much as a strong acid or strong base would. So what did increasing or decreasing concentration do to the pH? Well, if it was a strong acid, the pH went up a lot. Well, if it was a strong acid, the pH went down substantially, a lot, 2 times. If it was a strong base, the pH went up substantially, 2 times, more basic. However, if it was a weak acid, we saw that the pH went down, but not as much as a strong acid did, maybe by 1 time. And if it was a weak base, we saw that the pH went up, also less than the strong base, maybe 1 times. Lastly, let's go back to water and see what number is associated with water in terms of dissociation. Remember that water is equal parts hydronium ion acid to equal parts hydroxide ion base. That's what gives it that pH of 7. If we look at the actual concentration, the moles per liter of water, we see that there is 1 times 10 to the negative 7 moles per liter of hydronium ion and 1 times 10 to the negative 7 moles per liter of hydroxide ion. If we were to add those two together, you'll see that 7 plus 7 in the exponents gives us 14. And that's where our whole pH scale comes from, 0 to 14 as the maximum value, all due to water as our baseline. So then what we've discovered here is that the difference between strong and weak has nothing to do with the fact that the strong ones go to the gym and get pumped. Strength here has everything to do with the fact that the strong acids and bases dissociate or break apart, disconnect from each other completely. We can also call this ionization, when charged atoms, ions, separate from each other. In other words, we determine acids and bases based on when ions dissociate. So the definition you need here is that strong acids and strong bases create protons in the terms of strong acids, or hydroxide ions in the terms of strong bases for every single molecule present. 100% dissociation. That is the definition of whether or not an acid or base is strong. Some strong acids and bases you should be aware of are HCl, H2SO4, HNO3, HClO4, NaOH, and KOH. Contrariwise, weak acids and bases only create a fraction of the H protons or OH minus hydroxide ions for every molecule present. In other words, they only partially break apart, i.e. dissociate. Some common weak acids and bases you should be aware of are vinegar, acetic acid, HF, hydrofluoric acid. Fun story about that one. It's actually really dangerous. If you were to say, get your hand into HF, it would literally dissolve a lot of your skin and it would turn like this nasty ghostly white and burn you. So it's a weak acid, but that doesn't mean that it's less dangerous. It'll still dissolve all the skin off your hand. We have NH3, that's ammonia, the stuff in Windex, and HCO3 minus and CO3 minus 2, carbonate ion. That's a polyatomic ion. Before you move on to part 2 of this series in acids and bases, make sure you test your understanding of what was covered in this video. What are some differences between an acid and a base? And can you explain the difference between a strong and weak acid or base? Also, are the weak acids and bases safer to handle because they are weak? Let's wrap up these questions together. In this video, we learned that there is something called a pH scale that ranges from 0 to 14 in range of acid, red, which tastes sour, to basic, blue, which tastes bitter. We have a little alliteration for bases, and it goes like this: bases are bitter blue. And we're going to keep building on that in part 2 of the next video. We learned that we can determine if something is an acid or a base by using pH litmus paper, indicator solutions such as red cabbage water or poinsettia petal water, or pH meters if you want a more quantitative measurement. We learn the definition of acids and bases according to Arrhenius, where acids are something that create hydronium ion in solution and bases are something that create hydroxide ions. Then depending on how much hydronium ion it creates, let's say it dissociates 100%, we can say that that would be a strong acid. Or if it only partially dissociates, breaks apart, that would be a weak acid. And for bases, if it creates 100% hydroxide ions for every molecule of base in the solution, we can say it's a strong base. If it only partially dissociates or partially creates hydroxide ions in solution, then it's a weak base. And no, weak acids and weak bases does not mean they're safer to handle. As was the example with HF, hydrofluoric acid, would still dissolve all the skin on your hand. That's pretty dangerous, even though it's a weak acid. Please give this video a quacks up and subscribe to Duckonta for some more ducky content. For now, I bid you adieu, and I'll see you in part 2.
No ducks, no glory.